Okay, we're back and we're doing integrating this equation here. The integral from 3 to 5 x squared minus 9 to the 1/2 times x dx plus the integral from 3 to 5 2x dx. I'm working on this term a, which is a chain rule, the second rule there. A equals 1, u equals x squared minus 9, n equals 1/2, f of x equals x, and du dx equals 2x. I'm going to plug into the chain rule there. Well, don't forget, I'm still on this part here. Still working on this part. I haven't worked on that yet. I'm going to get u to the 1/2 plus 1 over 1/2 plus 1. F of x is x. Du dx is 2x. 3 and 5. This is x squared minus 9 to the 3/2 divided by 3/2. 1x over 2x is 1/2 between 3 and 5. When I bring this up, I flip it. 2/3 is going to be multiplied times the 1/2. The 2's cancel. I'm left with 1/3 x squared minus 9 to the 3/2. 5 and 3. I'm going to substitute this. So this is A. Substitute this into here. So this becomes 1/3 x squared minus 9 to the 3/2. 3 and 5. Take the integral of this. Simple power rule. X 1 plus 1 over 1 plus 1 between 3 and 5. This is my function y equals 1/3 x squared minus 9 to the 3/2 between 3 and 5 plus x squared between 3 and 5. Now I have to apply the fundamental theorem of calculus and figure out a number. What is the numerical value of this integral? So let's see. Y is going to be equal to, put a box, 1/3 5 squared minus 9 to the 3/2 minus 1/3 3 squared minus 9 to the 3/2. Now we got to close the box and work on the second part, second term. 5 squared minus 3 squared, and that's it. So now we have to work on this, and we got 1/3. And of course 25 minus 9. 25 minus 9, I believe, is going to be 16 to the 3/2. Minus 1/3. Notice we get 9 minus 9. So what do we get? 1/3. 9 minus 9.
I think you have the 1/3 twice. It doesn't matter.
Oh, yeah. No, it does matter. There it does. So 9 minus 9 is 0. So luckily this cancels out. Adding 25 minus 9. Okay, so what do we get here?
I think that box has to be closed too.
I think
Or you had an extra open. Yeah, there you go.
minus 1/3.
There we go.
Okay, I'm going to bring that up here because it's hard to do all these numbers down here. So what I'm going to get here is let's see if I can figure this out, because this is kind of messy what I did here. 1/3 21.3 minus okay, we get 1/3 21.3 minus 0 times 25 minus 9 is 16. That's when I raised it to the 3/2 power. So the answer here comes out to be 37.3. And once again, definite integral gives me a number answer. Indefinite integral gives me a function. Okay. Well, let's do another one. So we get these under our belt. Because a number of you had said that you were having problems with them. So we're going to do another one. And let's see. So let's erase this. And just follow these carefully because I am doing these in steps. So once again we have the integral of dy. You want to find the integral of x squared plus 1 to the 4th. Okay, times 4x dx. So that's a chain rule. So let's start to define our terms. A is 1. U equals x squared plus 1. N equals 4. F of x equals 4x. And du dx is 2x. Now we just got to plug into the chain rule. Y is going to be A, which is 1. U, 4 plus 1. 4 plus 1. F of x is 4x. And 2x. Okay, raised. I forgot to put the constants of integration here. To the 2 and the 4. Okay. So let's see what we get here. Plugging in the u. U is x squared plus 1 to the 5 over 5 times 4x divided by 2x is 2. That's going to be equal to 2/5 x squared plus 1 to the 5th between 2 and 4. Now what the fundamental rule of calculus says, just substitute in the 4 and subtract it from the 2. So y is going to equal to in the box 2/5 4 squared plus 1 to the 5th minus 2/5 2 squared plus 1 to the 5th. Notice if you wanted to, you could take the 2/5 and factor it out here. So you don't have to, you can apply it to the last thing if you want. I haven't done that. If I was doing this solving it by myself, I would do that. But, okay, so this is 2/5. That's 16 plus 1. That's 17 raised to the 5 minus 2/5. That's 4 plus 1. That's 3 raised to the 5.
5.
What?
You said it's 4 plus 1. That's 5.
It's 5. Right, 5 raised to the 5. Well, that's going to be 2/5. 17 raised to the 5. Where is my calculator? Ugh.
It's to the left of your monitor.
Is it? Where is? Oh, there it is. Okay, I should have this on the table here. Anyway, we're going to have 17 raised to the 5th. That's going to be a very large number. It's going to be 1,419,857. No zeros in that one. 5 raised to the 5th, I know what that is. It's 3125. Yeah, 3125. And let's see if my big function here multiplied by 2, that gives me 280, just say 284,000. I'm just going to round them off. Minus, okay, 1250. So 4,000 minus 1250, right? Okay. 4,000 minus 1250. You're supposed to subtract them, not multiply them. It's 2750. So 28,2750. And there's your value of y. It's a big number. It could be an investment. It could be anything. Should have closed this. And I forgot to close this. So. Okay. Well, that's the way you do it. The biggest problem here, where you're going to make your mistakes, it's probably not here. It's when you start to plug into these things. It's very easy to miss a negative. It's very easy to... So if you made a mistake like that, let's say you got down to here, I would take off 1 point at the most. Is this the second part of 3? Or the first?
I think it's 2 of 3.
2 of 3.
Yeah.
Okay. So the next thing we want to do is get into some examples from the worksheet on chapter 13. So let me erase this. Some of the examples we do, let me explain this a little bit, what we call flow examples. Now, suppose we have money flowing into a bank. Well, money doesn't flow into a bank on a continuous basis. Calculus is the mathematics of continuous functions. But we can assume over time that in the limit that money flows into a bank on a continuous basis. Obviously, each deposit puts a little discrete money in. But we can make that, if there are a lot of deposits, a lot of depositors, and they're close together within a particular time period, we can assume that it's a continuous stream. So we would want to know how much money gets deposited in this particular bank. And then we'd be given a rate of deposit, which is a derivative. And then we find the expected total deposits at the end of a certain period of time. That would be the function. So that's what we're going to use this for. How much time?
Like a minute and a half, maybe.
Okay, so therefore, let's put on the board some practical problems. And this is going to be from your worksheet. So I'm doing some of the problems for you. And this is going to be from chapter 13.1, number 34. It's called the flow of money. Okay, you have AT. I would say that would be A prime T. Is 100 e to the 0.1 t. Very similar to the one we had before. T is in hours. And this only holds for 10. Finished?
Yeah, wrap it up.
Okay. So we'll come back for another session of Wednesday.